So there is one more way to think about rotation matrices. One thing that is very practical. It'll help you a lot when you're using them in real life. So let's write one more time the general formula for the rotation from A to B. Okay. Let's look again at point P expressed in coordinate frame A. So we have P equals Px, Py, which really is shorthand for saying that P is the scalar Px times the unit axis x plus the scalar Py times the unit axis y, where x and y are the unit vectors that point in the direction of your axis. In this case, obviously, it's very simple because you have x, the x-axis is simply 1, 0, the unit vector 1, 0. The y-axis is just the vector 0, 1. So then we can write this relationship further in matrix form as x, y as the columns of a matrix times px, py. And then if we spell out the x and y column vectors, we just get 1, 0, 0, 1, px, py. Why did we go through all that trouble just to spell out the identity, right? Obviously, px, py is equal to the identity times px, py. Well, we can do the exact same thing, but we can choose two different orthogonal unit vectors as our axes. Why don't we express p relative to these two other coordinate vectors, x and y? And in this case, these unit vectors change. So the vector x, you can see, points in the direction of cosine theta, sine theta. Okay. The vector y points along the negative x-axis, so we're going to have minus sine theta, cosine theta. So now that we've replaced, this relationship still holds. Obviously, this relationship still holds. We just need to replace x and y inside of this matrix. So if we replace this by the new matrix having as columns the new vectors x and y, this is still true. Why do we care about this? Well, this picture looks a little bit familiar, right? It's as if the new vectors x hat and y hat actually define the coordinate frame B, and the original vectors define the coordinate frame A. So if x and y are the unit vectors that define coordinate frame B, then what we have is that the point expressed in coordinate frame A is going to be px and py in coordinate frame B times the axis vectors from coordinate frame B. Okay? So this is really the same as saying this further equals the rotation from A to B times PB. which is something that we've seen in the past. Okay? And the point here is that this is actually our rotation matrix from A to B. So the rotation matrix from A to B is comprised of the unit vectors indicating the new orientation of the axes in column format. So if someone gives you a matrix and says, this is a rotation matrix, what coordinate frame does it transfer me into? It's very easy. All you need to do is to look at the columns, and the column vectors will tell you the new orientation of the axes. Let's take a concrete example of that. I have my coordinate frame A. And somebody gives you the rotation matrix R from A to B equals 0, 1, minus 1, 0. What does coordinate frame B look like? Well, one thing you can do is I know the general formula for a rotation matrix. If I match these two, I can probably figure out what theta is, and then if I figured out what theta is, then I can apply that rotation, and I can see who B is. A simpler way to do it is to just say, well, the axes of B are just the columns of the rotation matrix. So the x-axis of B is going to be 0, 1 relative to A. So the x-axis of B is going to point in the direction of YA. So this is going to be XB. The y-axis of B is going to be minus 1, 0 in coordinate frame A. So that means the y-axis of B is going to point like this. And there you go. Now I've very easily drawn my coordinate frame B. Okay, let's look at another example. Let's get a different rotation matrix. So we have our coordinate frame A to start with. And then we get a different rotation matrix. The rotation from A to B is going to be negative 0.7, negative 0.7, and then we're going to have 0.7, negative 0.7. Okay? Who is coordinate frame B? Very easy to check just by looking at the column vectors. So XB is going to be this column. So XB is going to be pointing like this. YB is this column. So YB is going to be pointing like this. Let's quickly check that this works. So let's have a point in coordinate frame B. Let's say point 2, 0, for example. So 2, 0 in coordinate frame B, this point is right here. So this is P. Okay. Then that same point, expressed in coordinate frame A, is going to be the rotation matrix from A to B times the point in coordinate frame B. So if we just multiply this matrix by this vector, we're going to get negative 1.4 and negative 1.4. And you can easily check that that is indeed the location of P with respect to coordinate frame A. So the thing to remember from here, rotation matrix, the new orientation of the axes, you can easily see it as the column vectors of the rotation matrix. And that also gives new meaning to the characteristic that I was mentioning before, that rotation matrices are always orthonormal. Right? So the norm of any column vector is 1. That makes sense because the column vectors show us the new orientation of the axes. And the orientation of the axes, those have to be unit vectors. Also, the axes are always mutually orthogonal. Any two axes are perpendicular to each other. The dot product of any two columns of a rotation matrix has to be 0. OK, we're finally done with rotations, at least in 2D. We spent quite a while on them, but rotation matrices are some of the most fundamental tools that you use in robotics. You will use those every single day, so it's worth spending a little bit of time and just understanding all the subtleties. Now let's talk translations. And thankfully, translations are quite a bit simpler than rotations. Now, let's say that the difference between coordinate frame A and coordinate frame B isn't a rotation, but just a translation. So B, the axes have the same orientation as in A. There isn't any rotation, but B is translated with respect to A by Tx and Ty. So in this case, my point P, expressed in coordinate frame B, if I want to compute that same point in coordinate frame A, obviously all I have to do is add the two translation terms. So this is obviously very, very simple, but it doesn't quite get us where we'd like to go, because now what we want to do is combine rotations and translations. What if, and this is the most general case possible in 2D, where the between coordinate frame A and coordinate frame B is a translation and a rotation. And now we are talking about full transforms. So based on what we've so far, we can say that we can compute PA as being the rotation from A to B times PB plus the translation. This is correct. This works. But it's not compact. Furthermore, it's two operations. It's a multiplication and an addition, and it makes things extremely complicated, especially if you want to chain multiple such transforms. What if you have coordinate frame A, coordinate frame B, coordinate frame C, going from A to B to C, and so on, becomes very complicated if one transform is a multiplication and an addition.